Okay, we're back. Hopefully you went through that example. It all made sense. That was helpful. So on this slide, kind of have some of the same info as before. We're leading into something new for us. So if we start out saying gauge factor incorporates Poisson ratio, cross-sectional area, and resistivity. We knew that from the previous slides. So it says here one only needs to know the gauge factor and measure the change in resistance to calculate the strain, the axial strain. So that gauge factor, if you buy a strain gauge, you'll get that gauge factor from the manufacturer. So essentially you just need to put this into a Wheatstone bridge so you can measure the output voltage and you can get the strain from that. But we want to remember, like it says in red, that gauge factor is temperature dependent. So learning how to deal with that, that's the new thing we're going to cover now. First, let's just look at the temperature dependency. So here, this goes with this scale over here. So this is the gauge factor variation. This is just how the resistivity changes with temperature. So that's very linear, highly dependent on temperature relation. This other one, the parent microstrain, this has to do more with how the substrate, that electrically insulating substrate, and the metallic part of the strain gauge, how they change due to temperature at different rates. So you get this strain. Now we need to learn how to deal with these. These will both be present at the same time. We need to learn how to deal with just temperature effects in general. So let's start with this. The change in resistance total is going to be equal to the change in resistance from strain, which we're after, but then also the change in resistance from temperature. So we ask here, how do we calculate these? And ultimately, we want to know the second part, which is how do we tell if our measured change in resistance is coming from strain or temperature? So here, I just popped up a bunch of stuff to help us with that. Let's start with strain. So here's that equation for the gauge factor. And then let's just identify what this change in resistance is. It's the strained resistance minus the unstrained resistance. This is something you can get from the manufacturer. I'll show you a cut sheet soon. But we substitute that in for that, move the axial strain over here, and then we rearrange further because we're after the strained resistance. So the strained resistance is going to be the unstrained resistance plus the unstrained resistance times the gauge factor times the strain. So that is this. And then so the effects of temperature, this one here, we have the effects of temperature. It's kind of similar form to this part of this equation, but we have that unstrained resistance, and then we have this H, which is the gauge factor temperature sensitivity that we're defining over here. So this is the change in R per degree Celsius. Often this will be reported as a change in resistance, a percentage. You'll want to you want to divide it by 100 if it's like that, so that you're multiplying it by the true value of it. We'll do an example that shows that. That's the change in resistance from temperature. So the strained resistance is going to be the unstrained resistance. So this should be the total resistance. The total resistance is the change in resistance from strain plus the change in resistance from temperature. So total resistance, not resistance from strain. You need to update that slide. Then just want to point out this sentence is really important here. If the strain is compression, so everything we've talked about before would be tension, right? We're stretching it out, we're elongating it. But if we're compressing it, it shrinks, the resistance goes down, so we want to have a negative sign in there. This would be substituted up here if it was compression. So that's a really important point. Here is the slide that shows that cut sheet. So we have a bunch of different models, different strain gauges. Note some of them have 120 ohm nominal resistance or unstrained resistance. Some of them have 350. So that would be, that's some pretty common unstrained resistances. Then note that the nominal resistance is reported. So this is at room temperature, not 0 degrees Celsius. But typically we are interested in a change in temperature. So that point doesn't matter so much, but students ask. So I put it in there. The rest of these slides here are more how we practically deal with those temperature effects on the resistance. Before we get to that, I think this would be a good place for that other example. So I'm going to pause the video, go and take a look at example number 2.